A new generation of telescopes has made it possible to measure the specific gases swirling around planets light years away. For decades, our hunt for exoplanets relied entirely on watching for shadows. We could only detect a planet if it blocked a fraction of its host star's light, or if its gravity caused the star to wobble. Take the recently discovered GJ3378b, sitting 25 light-years away. We know it's a rocky super-Earth, but we only know it exists because of how it pulls on its star. The problem with this method is that knowing a planet's mass and orbit provides zero information about its surface. It could be a cratered, airless rock, or possibly a world teeming with biology. To answer that, the search for life is shifting. Instead of waiting for an alien civilization to broadcast a radio signal, astronomers are actively hunting for chemical signatures in the atmosphere. The primary tool leading this effort is the James Webb Space Telescope. Our focus has shifted from finding new planets to analyzing the specific chemicals that define them. This relies on transit spectroscopy. When a planet passes its star, a fraction of starlight filters through the atmosphere. Different gases absorb specific wavelengths, creating a unique barcode of dark gaps. Reading these gaps tells us exactly which molecules float in that alien sky. As a stress test for this method, astronomers pointed the telescope at TOI 561b. It's an ultra-hot, wet lava ball that orbits its star so closely a full year lasts under 11 hours. The extreme radiation was expected to strip away any surrounding gases. Instead, the telescope found clear evidence of an atmosphere clinging to this roasting rock. If this technology can read the atmospheric gases on a lava ball, it is capable of reading cooler, quieter worlds located in the habitable zone. That brings us to the Goldilocks zone, to Hycean worlds. These are planets with a dense, hydrogen-rich sky and a global liquid ocean. A prime target in this category is K2-18b, a massive exoplanet 110 light-years away. This is the transmission spectrum for K2-18b. The clear dips prove the presence of methane and carbon dioxide. Crucially, ammonia is missing, which strongly suggests a massive liquid ocean. And looking closely, a faint, overlapping signal indicates dimethyl sulfide, or DMS. On Earth, DMS is produced by living organisms, specifically marine phytoplankton. There is no known geological process that naturally creates it. The signal is still tentative and requires more validation, but this is the closest we've come to detecting the chemical exhaust of alien marine biology. To find absolute proof, we have to overcome a major limitation. To read atmospheres, current telescopes require a planet to perfectly transit its star from our viewpoint. If a promising rocky world like GJ3378b doesn't cross directly in front of its host star from our angle, its sky remains invisible to our spectrographs. To bypass that geometric flaw, astronomers are building the Extremely Large Telescope, or ELT, scheduled to come online in 2028. With a primary mirror 39 meters across, the ELT is powerful enough to capture the light reflecting directly off a planet's surface, removing the need for a transit. Simulations show that if biological chemistry exists on a planet orbiting Proxima Centauri, our closest stellar neighbor, the ELT could detect it in just 10 hours of observation. This timeline forces us to consider astroethics, the clear need for a moral and scientific framework to process and verify the implications of a confirmed biological signal. The tools we are building now will allow us to see which of our neighbors share the chemistry that defines life on Earth.